Hi, and welcome to our talk, Computer Vision, Separating the Weeds from the Seeds. I'm Shanti Greene, Master Principal with Daugherty Business Solutions, and with me today is Benjamin Weinert, Senior Data Scientist with Daugherty Business Solutions. We did this project in combination with KWS. KWS is a global agricultural firm that offers targeted varieties of seeds for multiple farmers to fit their operational needs, tailored to climatic conditions and other variables that you might find. Specifically, we worked with the Digital Innovation Accelerator within KWS. That's an area dedicated to collaborating with companies and organizations developing innovative digital solutions. Daugherty is a consulting company based out of St. Louis with 7 business units around the United States. We have over 1,200 consultants, and we're really technology focused. Within Daugherty, we have an innovation hub. That innovation hub focuses on exploring the latest technologies, things like artificial intelligence, and leveraging the brightest minds at Daugherty. The nice thing about what we do here is that we're not exploring technology for technology's sake. What we're really trying to do is explore new technology and link that to delivering business value. We want to make sure that our clients are getting the most out of new technologies. So let's talk a little bit more about this specific project and what we were trying to do. KWS was looking for an automated mechanism to identify weeds and target plants at multiple stages of development. So they can either be manually removed, so you want to pluck the weeds, or treated with herbicides. Farmers in the field need better tools to be able to evaluate what something is. They want to identify the species of that weed, and that created the need for a technical solution. This solution can inform decisions about if herbicide is required, and if it is required, what type of herbicide to apply. So what we want to do is look at something. In order to do that, we're going to apply techniques from computer vision. So let's look at the first thing we're going to do. We've got a picture of a weed, and we need to extract out of it just the picture of that plant. So we need to isolate the color space, kind of get rid of that background, mask the image off. So we need to remove the dependency on soil conditions, anything else that might be in there. If the farmer has taken a picture that might have multiple things in it, the eye can capture a lot of information. So we're going to do that color transformation, some morphological transformations, apply some masking, use contour moments, and sharpen the image. Now these are some really fancy techniques, so what we need is a fancy data scientist to walk us through that. Ben?
So I want to go over a little bit of the techniques we used in our pipeline to extract plants. To begin with, we used OpenCV. Now one of the first things you have to do is you have to determine the color space you're going to use. One thing to note about OpenCV is it translates your image from an RGB to a blue, green, red. Now that's important for 2 things. One is visualization, depending on the tool you're using. And the other is if you're using a pre-trained model. Some expect BGR, like VGG19, and some expect RGB, like ResNets. Now one of the things you could do when you're reading in the image is determine to grayscale it. You might think for determining plants versus weeds, color is important. And yes, it is. But there are intermediate steps that you need to take for edge finding, contour finding, etc. to extract out the plants. In this case, color doesn't really help as much, so you're going to want to grayscale it. This reduces the dimension of your data, making it easier for it to determine. So the next thing is morphological transformations. Now these are applied to binary image. First thing you have to do is decide on the kernel size and shape, which will affect what the transformation is. Here we have some common transformations to choose from. We have our original, script J, and then we have things like erosion, which shrinks your image. Now this is important for 2 things. One is it helps create more separation between your objects, and it helps highlight areas that you are confident are the foreground of your image. We have dilation, which is the opposite. It expands your object. Now that can be used if you want to make sure that you capture all of your object. Additionally, it highlights areas that you are confident are background in your image. Then we have some more complicated things like opening. Opening is an erosion followed by a dilation. Now what this does, if you look in the image, is it removes the noise in the image. The little white dots, because we shrink it and then expand it back to its original space, disappear. So we use this to remove some of the extra stuff that got caught from rocks or soil, etc. Additionally, it helps separate some of the plants from the stems and other plants in the image. Closing is the opposite. So dilation followed by an erosion. So what that ends up doing is it fills holes in your image that can get created when you're creating a mask for the image. And then there are other things like gradient, which highlights the edges of the image by doing the original minus an erosion. So once we have that, we want to extract out just the plant from our image. This is known as image segmentation. One thing you need to do here is change from BGR to the hue, saturation, value color space. Now, why do we want to do that? Because the same shade of color can look different depending on lighting throughout the image. A good example of this, the dress. If people remember that on the internet, was it black and blue? Was it white and gold? Turns out a lot of that had to do with the lighting in the image. So why does this help? Well, instead of having 3 color dimensions, it shrinks the color into the hue dimension. And then saturation determines how clear, how pure the picture is. Lower values are muted, higher values are pure. Value is the lighting. And that helps account for different lighting throughout your image. And once you do that, you can define a range, lower value and higher value in the HSV space. And use OpenCV's inRange function to create a mask we see in the middle image. Once you have the mask, you could just apply a bitwise and extract out the area you want. So for this, we used different combinations of green and yellow in the HSV space to extract out the plants. You can see here there's a little bit of the missing due to the fingers. This is where they could have applied a morphological transformation, like a closing, to fill in a little bit of that. So next, we're interested in contours. So contours are similar to edges, but they form a closed object. The idea behind it is you apply grayscaling to your image, you use an edge detection, and then you pass it to your contour finding tool. Why do we care about contours? Well, they have useful properties. Properties like image moments, area, perimeter, contour approximation, template matching, etc. So these are useful for feature engineering, which we'll get into later, but also in the extraction. They have a hierarchy. So you can notice here in the hand, you're probably going to find multiple contours, things like for the veins, the fingers, etc. Since there's a hierarchy to these, we can just say, only give us the outermost contour, the one that doesn't have any, that's not within any contours. Additionally, we use things like the image moment and the area to extract only the plant that was closest to the center and matched a minimum size. So, Shanti?
So in this slide, you'll take a look at what's some of our actual data. The image on the left is a raw image that's been taken, and the image on the right is what happens after we've applied a lot of those image masking and segmenting techniques. So you'll see that the background has been removed, and you have just the important parts of the plant. You've got a good picture of the leaves, you still understand what color they are in that color space. And what that's going to allow us to do is do some feature engineering, and we're going to start extracting features. So there are 3 categories that we were looking to extract features in: the color, the shape, and the texture. And we created features such as the percent of the image that was stem, or the solidity, so how much the picture of a leaf might match within a specific oval. What that's going to allow us to do is proceed on to our next step and build some sophisticated models, for which we will need a sophisticated data scientist.
So I want to talk about convolutional neural networks, because that's what you think of when you think images. But why? Why do we always use CNNs? Additionally, a little bit about how they work. So on the right side of the image, you see a normal or dense or vanilla neural network. What is it? It's just a set of layers of neurons. Each neuron just takes a linear combination of the inputs and applies a nonlinear activation function. Through backpropagation, the neurons learn what weights to use, and these help them determine certain features that might be helpful in identifying the image. So, for example, the top neuron might be looking for vertical lines in the image. But since it depends on the inputs in the image, it's looking, let's say, vertical lines in the left side of the image. The next neuron might be looking at vertical lines in the right side of the image. Now, to you and me, a vertical line is a vertical line. It doesn't really matter where it is. So you can imagine, for this, it's a pretty straightforward image. But the more complicated our features are and the bigger our data, you can imagine the parameters kind of grow out of hand here. So that's where convolutional neural networks came in for 2 methods. One is to reduce the parameters and also to remove some spatial dependency. So to do that, instead of having the neurons be dependent on the input, we use filters. Each filter looks for a specific feature in the data. Again, learning this through backpropagation. Now, instead of being dependent on the inputs, the filters will move along the image, highlighting where that feature they're looking for are in. This way, it doesn't really matter where the vertical line is. You just have a filter that looks for vertical lines. This reduces the parameters in your image drastically. So what you see here is we have a bunch of different filters at each stage, each looking for a different feature. Then also, as you go along, you kind of see that the spatial dimensions of the image shrinks. It starts out at 28 by 28, goes to 14 by 14, 7 by 7, etc. So why is it doing this? Well, it's doing this to remove some of the spatial dependency. As we move along the image through convolutions and pooling layers, we're increasing the receptive field of the image, of the filter. So what that does is now each pixel in the smaller version represents a bigger area in the original image. So this kind of removes some of the spatial dependencies. Now it doesn't exactly matter if the 4 drawn on there is perfect. It could be tilted, it could be shifted, etc. But since we're removing some of that spatial dependency, it doesn't need to see every variation. Now, just like with a normal neural network, the more layers you have, the more complicated the features that the filters look for are. Why don't we just make giant neural networks? Well, turns out it's really hard for information to propagate backwards. So for that reason, we started looking into architectures that are meant for deep neural networks. Additionally, a lot of these neural networks come with pre-trained weights so that we can start using that with transfer learning instead of training from scratch. So the first thing we looked into were ResNets. So again, the idea behind this is we want to be able to have a deeper neural network without running into the issues of not being able to pass information backwards. So how does this do this? Well, on the left here, we have the VGG19, which is a older neural network structure. Then we have a 34-layer plain residual network. Now this has more layers, but it's going to be harder to pass back some of the information, so it might not actually be better. That's where the residual block comes in. So what the residual block does is it takes the input and it moves it along 2 separate paths. One goes through a set of convolutional layers, in this case 2 convolutional layers. The other uses a skip connection and goes around it, and then combines with it at the end. So this does a few things. One is it gives a very easy path for information to travel all the way through your model. It's just the identity. Because there's an easy path for information to travel, we avoid the vanishing gradient problem, and we can have deeper layers, since there's always some way that it could travel backwards. Another thing is now it's not learning a new mapping for each layer. What it's really learning is the difference, or residual, from the input. And that ends up actually being easier to use. Again, pre-trained versions of this can be used for transfer learning, so this made this attractive. So another thing was the inception model. So this was actually based off of the meme. We've got to go deeper. It's, I think, the only paper that actually cites a meme. I don't know. It's 2020. There could be more now. So the idea behind this is that images can have multiple scales. We can have a plant at the foreground of the image, or it could be off in the corner and small. So this is important because we have to choose the filter size. Do we want a 1 by 1, 3 by 3, 5 by 5, etc. So that the filter size determines kind of what features to look for. It's how much of the image are you looking for at a time for a feature. So instead of now picking that out by ourselves, the idea is let's build an inception module that allows the model to do it for us. What happens is the input gets split along multiple paths, sent along multiple paths, and it goes through different filter layers. You see a 1 by 1, a 3 by 3, and a 5 by 5. At the end, when it goes through that, they recombine. The idea here is that the model will figure out the best filter size and can handle different scales in your image. Now, that's just going wider. To allow it to go deeper, the idea is they added auxiliary classifiers to handle the vanishing gradient problem at different depths of the model. Early on, that helps with that. Towards the end of training, it's more of a regularizer. So here we have the full inception model. You can see there's a starting point at the beginning called the stem. Then it's just a bunch of stacked inception modules. And we have the offshoots at different sections of the model so that it can prevent some of that vanishing gradient. So finally, we looked into the exception, or extreme inception. Of course, it's named that. The idea behind this is it uses separable convolutions instead of a normal convolution. So at the top here, we have a normal convolution. You see we have a 12 by 12 by 3 image, and we apply a 5 by 5 by 3 filter. Now what this does is it works along the spatial and channel dimensions. This leaves us with an 8 by 8 by 1 output, and we apply 256 of these. So that is 5 times 5 times 3 times 8 times 8 times 256 calculations for this one layer. That's a lot. And again, that's one layer. So let's try reducing that. The idea is let's use a depth-wise separable convolution and a point-wise separable convolution. So the depth-wise takes the 12 by 12 by 3, and instead it applies 3 5 by 5 by 1s. So what that does is now we're only working on the spatial dimension, since each of the channel dimensions gets its own convolution. That leaves us with an 8 by 8 by 3. Then, after that, we take the 8 by 8 by 3, and we apply a 1 by 1 by 3. Since that's 1 by 1 in the spatial dimension, it's only working on the channel dimensions. And we use 256 of these to get us back to the original 8 by 8 by 256 output. Turns out, by doing this in 2 separate stages, it's actually a lot fewer parameters. In this case, it's about an order of magnitude of 25. Why do we care? This means we can go deeper with fewer parameters, so it's easier to learn. Because of that, we actually decided to use the exception model. And here we have the full exception model. You can see they put these separable convolutions within residual blocks. So it's kind of taking a little bit of multiple types of models. Finally, one of the things we looked into were attention gates. Now, attention is something that I know of more from natural language processing. What it does is it suppresses feature responses in background regions. In NLP, basically what that means is if you're reading a textbook and you want to learn about something, do you read the entire textbook and try to remember the important parts? Or do you go to the table of contents, look at the chapters you care about, and only read those? That's kind of what it's doing. For images, instead, it kind of creates a heat map. The heat map highlights to the network or your eyes what are the important parts of the image that I need to care about. How does it do this? It creates attention coefficients. Each coefficient is applied to a pixel, and it highlights how important is this pixel. And the way it does this is it takes global features from a more coarse granularity in your model and your current feature map, your local features, and combines them. This highlights kind of what are the important areas in the image. Applies an activation function, reduces it to a single channel dimension, and applies a sigmoid to move every pixel between 0 and 1 for the coefficients. Then it just multiplies your original feature map by these attention coefficients. So here's the paper that originally mentioned these. It was looking for the pancreas in medical images. So what we have here is the original medical images, and it's the attention coefficients as a function of the trained epochs. And you can see over time, it highlights the spleen, the kidney, and the pancreas.
So Ben, which one is the spleen, the liver, or the pancreas?
Damn it, Shanti, I'm a PhD, not a doctor. Too hard to resist. I apologize to my wife. So we ended up applying these attention gates to the output of the exception model. Shanti?
So now we've got a really nice neural network that's doing a great job of helping us differentiate between the target plant and the weeds. But we think we can do more. So what we want to do is combine that neural network with an additional classifier. And what we're going to do in that additional classifier is use our ability to talk to subject matter experts and figure out what they're looking for when they're doing this as a manual process. So KWS has a subject matter expert in botany, and we're working with him to help understand what he's looking for when he's looking at a plant. Is he looking at the shape of the leaf? Is he looking at texture of the leaf? How much is the ratio of the stem to the other parts of the plant? We took that information and we were able to create features based on his input. We're going to use that in addition to the neural network and feed that into a multi-level hierarchical classification. So we found that at some growth stages of plants, that addition of the top layer had a really significant improvement in our model. So let's look at a few of those features. So in correspondence with that subject matter expert, we talked about things like the color. We understand that the color of the leaves is really important to differentiating what type of plant something is. We looked at some of the texture, the dissimilarity, the correlation, some of the entropy. A lot of work around the shape of it. So how many objects are we detecting in that picture? Give us a feel for how many leaves there are. The area of the plant, how large are some of those leaves, the aspect ratio, some of the bounding shapes. Try and tell us about, is this a pointy leaf? Is this a round leaf? And then we looked at some parts of the model. Like, should we include the neural network output with the classifier, this histogram of oriented gradients, and we're going to put those all together. And we're going to create a custom grid search for this. Now, often when people use grid search, they're trying to find the best model parameters, things like the learning rate, the regularization, activation functions, and dropout. But we built a wrapper around grid search so we could really customize that and add in structural parameters. So how many trainable exception layers should we be using? The attention gates, classifier features, but most importantly, the neural network versus the neural network plus the classifier. So we were able to pick out where we're going to need that hierarchical level and have the additional classification, and where the neural network is performing on its own. So this was a really nice addition to just having a plain neural network. All right, so the big question, how'd we do? We think we did really well. So we achieved over 91% classification accuracy in every stage, with a best classification accuracy over 93%. Now you might be thinking, well, 93 is not 100%. How do you know if this is good or not? Well, in talking to experts, PhD students in botany at some stages of development can only identify these weeds versus the target plant with about 85% accuracy. And at all stages, we're over 90% accurate. So we think this was a really successful project, and we felt really good about both how we did it, so the structure of the model, the methodology, and the actual results. But we don't want to leave it there. As we talked about at the beginning, we don't just want that binary classification. Is it a weed or the target? We need to know what species is that weed. So let's extend our work. Here we're going to test the idea of multi-class. We'll look at each species of weed as a separate class and our one target plant. So our original model focused on that binary classification, and now we're going to reframe this. Preliminary results found that multi-class actually performed better than that binary classification. Why is that? Well, at different stages in development, the weeds sometimes resemble each other. At other stages, the weeds might resemble our target plant. But that information was all getting lumped together when we were just looking at weed versus target. This gave, when we spread it out, we actually had more classes, and the model was able to pick up and differentiate those different things. Now, this was not without its challenges.
So one of the challenges was we're dealing with plants. And plants have to grow, especially at different stages of growth. That limited the availability of images. So for certain stages of growth, we had a ton of data for one type of plant. Others, we had fewer. So this led to a lot of imbalanced data. So we looked into multiple imbalance techniques. Oversampling, undersampling, we created synthetic data, and then we even weighted the loss function. What we found was that the weighted loss function performed the best. It was also the quickest option for us. One thing to consider in the future is focal loss. So for the weighted loss function, you still have to pick the weights that you want for each class. Focal loss, on the other hand, takes how well you worked on that image and uses that as a weight. If you performed very well, it's a low weight. If you performed very off, it's a high weight. So that would do that automatically. So another thing we looked into was imbalance within a class. So instead of just weeds versus plants, we have 3 stages of growth for each plant. So what we did was, instead of building a model with n classes, we ended up building a model with 3 n classes for the 3 stages of growth. We weighted each of the 3 n classes appropriately and trained our model. Then, when we wanted to predict and measure the accuracy, we recombined into the original n classes. What we found here was a significant boost in accuracy. For us, this was easy enough to do because we had subclasses in our labeled data. But some things we had considered were using a feature detector to create some feature vectors of the image, and clustering in case we didn't have multi-labeled data. So, Shanti?
So some of the key takeaways from this project are, yes, we're able to determine whether something was a target plant or a weed, and we're able to determine specifically what's that species of weed. We found that combining the neural network architecture with attention gates and the classifier increased our accuracy in specific stages. So working with a subject matter expert was incredibly valuable in helping define custom features to give us the best classification. Finally, weighting the loss function and splitting within the class was the best method for handling this highly imbalanced data. And that's a big takeaway for us, and we think that that was really important. Thanks for taking the time to be with us today. If you've got questions, please join us for our Q&A session.
Good afternoon, and thank you so much for joining us for the live Q&A session following the computer vision session. We hope that you enjoyed the session and that you have some questions and some discussion topics that you'd like to engage with our presenters. My name is Antoinette Boyd, and I serve on the Workforce Development Committee for Prepare.ai, and I'll be moderating our question and answer session for this afternoon. So we are so pleased to have our presenters here, Benjamin and Shanti, and they are live and ready to answer your questions and engage in any discussion topics around their presentation that might be of interest to you. So if you have any questions, please feel free to pop them in the chat, and we're here and happy to share any information or thoughts related to your questions. While we wait for some questions to come in from our audience, Shanti and Benjamin, would you mind sharing what are a few takeaways from your session? So for someone like me who is new to this topic, but it's very interesting and fascinating to me, what's one key takeaway for that you'd want attendees to know from your session?
Yeah, so one of the most interesting things was, yes, you can use computer vision to identify species of plants. That was an interesting question going in. We didn't know if it was going to be possible. So yeah, you can definitely do that with a pretty good degree of certainty, over 90%.
I think what was interesting to me was the combination of just pure neural network technique. So using the exception network with some additions to it. And talking with the experts to kind of figure out what they're looking for. Adding that together was incredibly helpful at certain stages of the growth. And we were able to gain a decent amount of accuracy by discussing those features.
Yeah, I think that's a really interesting point. We often talk about the importance of having subject matter expertise, and is it that your data scientists need to come from that domain and that field and be subject matter experts, or can they just consult with subject matter experts, get some of that information, synthesize it, and then use that to build their features? So we went that latter route. We worked closely with a subject matter expert, but none of us are botanists. But we're able to translate what he was telling us and what he's doing with his eyes and his expert knowledge into a computer algorithm.
Wonderful. Thank you so much for sharing those takeaways. Let's see if we have any questions here. Doesn't look like we have any questions yet, but we do have some people here on the call, so don't be shy. If there's something that was interesting from the session that you'd like to share, you can feel free to pop that into the chat. Or if there's a question you have for our wonderful speakers, we do have some time here to engage in some more detail regarding their session. So please don't be shy. Put your question in the chat. We're here and we're ready for you.
Or if our session just had the best moment of levity in your day, feel free to let us know that you really enjoyed that and that you'd like Ben to start learning how to interpret medical imaging.
I'm interested. An interest that I didn't think I'd ever have, but I was intrigued by the session. Like I said, a lot of it is sort of kind of foreign language to me, mixed in with some things that I'm aware of, but it was very intriguing. It makes me want to research and learn more and figure out, for someone like myself who hasn't engaged in this, what are some things that I can do to become a little bit more educated on these topics or even engaged in this sort of research.
Yeah, I think thinking about how you decompose a big problem like this. So when you start with a question, can you train a computer to identify 2 species of plants? Learning how to decompose that into smaller problems. Okay, like what does a picture of a plant look like? How do I identify the different elements of that plant? What are they? So you start with that piece. Okay, I've got that. How do I create features out of that so that this is something that I could train some sort of model to build, whether that's a neural network or a traditional type of model? for a classifier. And then you start putting those things together.
I'd say the starting point was just, okay, how do we, knowing that probably if we gave this to a farmer, there'd be a wide variation in soil. So it was the reading in an image and trying to extract it and going through OpenCV techniques and just kind of seeing what was out there. Then I guess looking into neural networks. Since we've done this work, there have been 2 big updates to pre-trained networks out there. There's BIT, which is one of Google's networks. I think it's Big Transfer is what it stands for. And that has had some great results. And as of a few days ago, there's a new paper called An Image is Worth 16 by 16 Words, because they always have to have some sort of punny title.
Mm-hmm.
And that uses transformers. So I mentioned a little bit about attention gates, how we added them in. In natural language processing, LSTMs were used for the longest time for reading in sentences. And then, like I had here, you added in attention gates. What they slowly learned is that you don't need the LSTM, you could just stack attention gates and transformers. And that's been a huge thing in NLP. As of a few days ago, there's now a neural network that uses just stacked attention transformers instead of convolutions. And in the results I saw in the paper, it looks really good and can be trained nearly order of magnitude quicker depending on how big the model is that you make it. So kind of just going out what's out there is a really useful thing. Very few things are trained from scratch right now because data, having a ridiculous amount of data is kind of how you do all the pre-training. In the paper for BIT, I think it was 2,500 TPU days to train. Obviously, we're not going to be able to do that. But what you can do is you could take that initial set of weights and add to it, which will speed up your process drastically.
Wonderful. Thank you for that additional insight. Certainly appreciate it. So it doesn't look like we have any additional questions, so we can go ahead and wrap up the session. We want to thank Mr. Benjamin Weinert and Mr. Shanti Greene for their expertise and their time in hosting the session and also being here live to answer your questions. We are hosting events through Prepare.ai throughout the month, and we hope to see you at some future sessions. Thank you so much for attending, and we hope you have a great afternoon.
Yeah, thanks for watching.
Thank you.
Thank you.
Have a good day.